Great. So first, welcome everyone joining this webinar, 3D printing in space exploration and aerospace from Markforged. And I would like to introduce today's presenter. So this is an event collaboration between Markforged and Central Innovation. And myself is Alan Yu, Application Engineering Manager of Markforged APAC. And today we're also very happy to have Damian Murphy from Central Innovation and Martin from Central Innovation as well. So they will introduce a little bit more about themselves when they speak. Before we start, just want to let you know in this Zoom platform, if you look at the toolbar, there's a Q&A tab. So during the webinar, if you have any questions, please feel free to write down your questions there. Our team will reply immediately, or we will save the question to the end of the webinar and we will answer them live. Right, we have a lot of content today, so let's dive in. So first we will start with space exploration, right? So it's a new age of space exploration. Basically, there's some questions that we want to answer, right? We have been spending a lot of resources and money and time throughout the human history to answer questions like who are we, why are we here, where do we come from, what is our purpose, and the most important is, are we alone, right, in the universe? So these are great questions, and but it's kind of difficult to answer. To answer this question, you must look through a different perspective, right? So we need to look a different way to answer this question, not within the space that we have. So you can see throughout the time, right, human is looking through the sky and look at the Earth itself, the solar system, and observe what's happening out there. So that means we need to have much more powerful tools, right, like telescopes, satellites, space probe. We need more rovers because we are now able to send rovers to another world. And definitely we need a better launch vehicles to carry all these equipment and apparatus to the space. And recent decades is really hot about finding the extraterrestrial life, right? So we want to know whether there's planet out there, and now we have answered that there is a exoplanets out there, right? And we want to also land probe in the gas giant around the solar system, and we're not talking about interstellar travel already, right, to explore the nearest exoplanet close to the Earth. And so we're building spaceship, spacecraft to do these things. Yeah, so we also want to do like more space stations, so we can do more things in space environment, right? We need to have a more sophisticated apparatus in the space area. And extend the travel, because like we're talking about bringing people to Mars, right? That's talking about 4 years travel. And also we need to have a station, right? If we're going to live in the moon or in the Mars. So all of these require hardware, right? We need to do more probes. We need rovers, carriage, vehicles and vessels. And then we're talking about interstellar here, which is one of the hot topic, right? The sail that can travel in a very high speed. And then we're building this incredible space telescope, right? James Webb telescope has been building for 20 years. Space station in the moon, station in the Mars. So that's actually not just physics, right? Everything is physical, right? You need to have a hardware to do all this challenging work. So the challenge also comes with the making this part, right? Like everything is a single piece, right? We do one time, and a couple years later we have a new version, right? So that's a challenge. Like we're not making mass production. Everything is, you need a lot of a prototype, and you only build one end use part, right? The final part. And sometimes you're using that prototype as the product. And every different part means there's a different product, different cycle, right, for each single part. And that requires a lot of work. And everything we try to do is the first time we do it, right? Because the space exploration used the most top-notch technology we have in human history, right? And a lot of technology we use today is because we are trying to build this incredible equipment. So we always use the latest technology and design technique to push the limit, right, of what we can make. So these projects are normally for the collaboration around the world, right? It's not like single country, single team can achieve. So the communication, working with all around the world is also very, very important. And some of the mission take a very long time, right? When we send a probe to the edge of the solar system, talking about 20 years, right? And we need to be able to maintain the project with the parts, spare parts, the system have to be working, very reliable system. And that is very difficult, right? When you have all these projects going on at the same time. So imagine how much inventory and part you need to maintain. So there's a lot of challenge over there as well. So today we will investigate some of the case study, like how this team is using Markforged technology to achieve some of the goal, right? And also you need to have very good software to do this. And at the end, maybe we'll talk about why Markforged is a good way to go with all this. So some reference here. For example, there's a project between NASA, MIT, Caltech, and KAIS from Korea in APAC. It's actually they inviting different teams around the world to build a robot that can be able to explore some kind of underground world, not in Earth, but like maybe in the moon or in the Mars. And one of the team is actually leveraging Markforged technology to build this sensor carrier, right, in this robot. So so the inside this fixture actually is the lighter, and this is basically the most expensive piece of component of the whole thing, right? So they know in the uncertain world there's a lot of risk and there's a lot of challenge, and you need to protect this incredible expensive component. And because you're not able to replace it, right, when you send it to a different world. So they need to have a reliable protection system. And what they choose is using Markforged technology, which they can build a very sophisticated, complex geometry. At the same time, it's lightweight and very strong. And they can do the work with protecting. The work of this robot is going to be very robust, right? It has to be very robust. So that's where to go with the Markforged. The one thing good is they also can bring the printer into the field, right? Like in the testing environment, they'll be able to adjust the design and make the part immediately. So this is another angle. So they printed with a full Markforged using an honest material with continuous fiber reinforcement. So they brought them to the competition site, right? To make not just this part, but also some other part, and they evolve during the process. And we also have a great case study from Australia as well, right? Xtech is a company who focus in the military application and also expand the solution to space exploration. So here is actually they are building a carrier, a satellite carrier fixture in a rocket, right? So actually they need something fast and strong and reliable part for them to build their prototypes. So basically the part right here you can see is the number 3, right? So that is the club set, how it looks like. And actually they cast the prototype last week in the Landforce show in Brisbane. You can see here all the black stuff, the black color part is actually printed by Markforged. So this is a great proof of concept, and they can do some kind of a testing to see whether the design work for certain environment. And the reason they choose Markforged is also because it's very convenient, it is strong, can do the job they need. So they actually printing daily, and they have a significant reduction in the product development cost, not just the cost per part, but also the time that involved to getting the part as well. This is another customer from Australia as well. They actually helping to build the telescope, the radio telescope, right, for space exploration. So basically what they need is they need to have a holder to hold the sensor, right? They have like originally using a machining aluminum, which you need to machine like 29 components and then assemble them together. So now they were able to use Markforged to print in one attempt and be able to hold like a very big number of sensor. So they have also tried to print this using other material. However, those material is just not strong enough to do the work. So here you can see how it looks like. You can see all the sensors on the table, and here is the black page printed by Markforged, which is strong enough and lightweight, and they get trust on this, and it actually is a end-use part. So we have talked enough about the space exploration. So how about like closer to us, right? Aerospace. So in aerospace, also they also turn to additive manufacturing, not recently, but for quite a long time already, right? One challenge of aerospace, also similar to space exploration, is like everything is very small quantity, right? If you look at the data, right, the fighter jet, or even though the commercial aircraft, there's not that many that we have built in the history, right? The largest number we have built is probably maybe A320. So far, we have just built around 9,000 aircraft. And all of this aircraft is expected to run a very long time, right? 20, 30, 40 years. So the maintenance is very challenging, right? A lot of things that we used 40 years ago, we don't use that anymore, right? We don't have that anymore. Even the drawing and the mold to make them, maybe it's long gone, right? So it's very difficult to find that, and sometimes you need one part, and that part may just define whether the aircraft can fly or not. Right? And for those, you really need a very quick and easy solution. So basically, the aerospace industry using the additive manufacture, small batch production, also distributed manufacturing, because the aircraft fly around the world, right? You cannot just have all the inventory in one place, which is making the whole process very difficult. So what you want is like every major station, you will have capability to manufacturing all those parts. So that will be the distributed manufacturing. Yes, I mentioned about aging aircraft repair, right? MRO, often like original tools are already long gone or damaged, and you won't be able to make the part without those tooling. But now we make those tooling or make the part directly using additive manufacturing method. And recent year also, we were advancing the technology, so more composite materials used in aircraft. And one challenge is also you need to make the tooling for the composite process. 3D printing will also be able to ease the pain. So some cases here, for example, Ripping Insights Republic. So this company majorly serve customer with smaller aircraft for retrofit and improvement. So for this project, basically they use Markforged to print the whole dashboard of the aircraft. And the accuracy they will be able to achieve in the ±1 millimeter, which is incredible for the size like that. In additive manufacturing, normally the larger the size, the worse the accuracy or the tolerance you will get. But Markforged will be able to maintain a very high accuracy, even though you're doing a very large part or you're assembling a different part into one pieces. We'll be able to maintain the shape because with a fiber reinforcement that we can maintain the shape very nicely. And also the accuracy of the part in general is very good. So this is a top flight aero structure. So they specialize in small part production and also making toolings. So because it's small part, right? So there's a lot of toolings, and they're using our composite material also to pre the hydraulic press die, and this die can withstand 100 tons of a compression force, which is very, very good in terms of using composite material, not metal material. And then we have this Tetron company also. They're helping Science Aerospace Research Center for this research project to develop a new wingtip. So originally the design they have is like impossible to make. Either you use an EDM, which is going to be very, very expensive and take a very long time, or you're using an additive, right? So in this case, they're using our metal printing technology to produce the part to the spec with an intricate design and without any problem compared to EDM, right? Or the original goal to achieve. And the cost would be like a fraction of the cost if they do with an EDM way. J.J. Churchill for precision inspection of some very expensive part, for example, like this turbine blade, right? And more importantly, why they use Markforged is you need a strong part, but at the same time, you don't want to make any scratch, right, on the component you're doing the inspection, because make a scratch of this expensive piece of a component is a huge cost, right? So for them, they don't prefer to have a metal material to touch with this part. So they choose to use a composite material from Markforged. At the same time, they want a strong, right, in nature, so you can hold the shape, hold the position nicely, and do the day-to-day work. And a composite printer with fiber reinforcement to Markforged can do the job, right? Lightweight, strong, at the same time, non-marring. And we have this also a fighter jet case study from US Air Force, right, Marine. So basically they have this F-35 stealth fighter landed with a problem with the landing gear. The original method is you have to go back to the OEM, and even though you have a small part, you need to replace with the whole assembly, right? And the whole assembly talking about 70,000, and we're talking about like 4 or 5 months lead time. Performance lead time, or I mean 70,000 maybe it's not acceptable for them, but like 4 to 5 months lead time, it means that the fighter jet have to be landed for 4 to 5 months. That is a huge cost, right? That's even cost more than the 70,000. So in this case, they were able to print these small pieces using Markforged composite fabric reinforcement technique, and then get the plane go back to usage, right, in just a days. And also the cost is like not even a fraction of the original 70,000. And that's a huge advantage for them. Finally, there's a bracket you can see from I'm not sure this aircraft that flying in the space, but you can see the black part right here. The bracket is printed by Markforged. So some other high value aerospace or space exploration application, right? Lightweight cabin components, brackets, harnessing, sensor mount, precision inspection, tooling, holding, functional prototype, and some of the hardware like turbo hardware will be possible with a Markforged technology. Right, so accuracy is very important. So recently, like 2 months ago, we launched this first AI-powered software in additive manufacturing world. It's called Blacksmith. Basically, what it does is, we're going to skip the video. So you can see here, we actually have a laser scanner attached to our print head. So when you're printing, at the same time, we're measuring the actual printing itself, right? So we'll be able to generate, count point data, right? After you finish the print, you have the count point data of the physical part, and you can compare with your CAD. And that learning can get back to the software. So next time, you'll be able to get a more accurate part, because the blacksmith will be able to adjust the printing pathing according to the inspection result, which is new. And we're the first in the additive manufacturing world, right? So yeah, we will, just like the machine skill, we already can cancel all this variation in the production of the hardware itself. And we close the loop, right, by printing, scan, and adapt the result of the scan to make sure you have a better printing next time. Right, so it's the part you can trust, right in the first time, and you don't get this problem of dripping away because you use it for a long time. So streamline low-cost manufacturing method. I think I have explained enough. So Damien, are you ready? Maybe you should take it away. I will stop sharing.
Thank you, Alan. It was lovely to listen. I don't think I can start my video. It won't let me. It says, but maybe you can turn that on.
Are you able to share?
It says the host has stopped it.
Yeah, maybe you need to promote Damien as a co-host.
It's okay. I can do it without a video otherwise.
Okay, I was just going to promote as a host. Is that okay now?
think you'll be able
Yes.
Yeah.
Excellent. Okay, thanks very much, Alan. It's my pleasure to present today. As Alan said, we're short on time, so I'll keep it quick. So for those of you, some of you may have met me already. I work for Central Innovation, which Intercad is part of. Some of you may recognize that. I'm actually an engineer. I worked in aerospace for a number of years, and I've had the pleasure of heading up the simulation team at Central Innovation. Okay, so today my presentation is going to be supplementary to Alan's. It's going to be into two parts. One, I'm just going to talk a little bit about Central Innovation really briefly. We're going to talk about how simulation is used in engineering. It's a really large topic, so there's other aspects for carbon fiber simulation that we won't cover, but I'm happy to answer questions. I'm going to talk a little bit about how we iterate our design to achieve our goals, and a little bit of how we used to do that and how our new tools and systems allow us to do that in a new way. I'm going to talk about some of the non-obvious ways of doing these iterations using virtual simulations. And then the second half will be introducing a tool called topology optimization. Talk about how do we automate these types of design iterations. And
we're not looking at, are you sharing the screen or something?
Let me share that again. My apologies. I thought I shared it, but share. Can you see my screen?
You can see now. Thank you.
Sorry about that. So briefly, yes, an intro to CI. Talk a little bit about the use of simulation in engineering, traditional manual iterations. So how do we achieve our goals for our, why are we doing these types of iterations, and how do the tools let us do that? Then we're going to talk a little bit about some of the aerospace specific ways of simulating to achieve those goals. Then we're going to introduce topology optimization. It's just automate these iterations, and introduce how the manufacturing process and constraints, how those have been freed up, and 3D printing actually lets us create geometry in a different way. And then I'm going to hand you over to my colleague Mark, who will do two brief live demos. Like I said, it's a large topic, so I'll go quite quickly. Feel free to send questions in. So those of you that may know us already, Intercad, we're a supplier, the largest supplier of SolidWorks in Australia and New Zealand. We also supply a number of other tools across the architectural industry, hardware, the world's fastest workstations. We provide systems integrations for people who want to connect their CAD through to the ERP and other systems, and recruitment solutions. Probably the most important aspect of what differentiates us is that we employ qualified engineers. We have many, actually this is a little bit out of date, we have more than 8 elite application engineers on staff. I myself come from aerospace. I worked as a stress engineer in the UK for military aircraft for a number of years, and I've looked after simulation teams across Australia and New Zealand from time to time in different places. So first, okay, let's talk about the use of testing and simulation in engineering. So why do we do this stuff? And it's because we're trying to meet a goal. Okay, we're trying to meet our design specification, stop things failing, make sure that we don't kill people. And often we'll use physical prototyping to make sure that whatever we make doesn't break. Okay, and we get real world results. Maybe we'll use these to pass standard or specification. So our 3D printing fits well into this because we can produce products much more simply. However, we can do detailed virtual design validation. What happens when we have really complicated loads that are hard to simulate? Vibration and other things, we have to use shaker tables. When it's apt to be expensive, components can be expensive to build. So we can actually do early iterations virtually and save time and money. And it allows us to create realistic analysis models. So This is the realm of aerospace, and we can use simulations to answer our questions, make a virtual replica of what we're building. The last type that we talk about is early virtual prototyping. So early in our design, as a designer, when we're trying to make decisions, does it meet the requirements? Does it meet our stress, deflection? Do I need another bracket? Do I need another gusset? It enables us to make those decisions quickly, produce faster product developments, improve the quality and the performance of our products, because we're making good design decisions as we go. And often you should ask these questions when you're thinking about, how do I change my product? How do you know what you've done is good enough? How do you know it can't be better? How do you know it can't be lighter? When are you going to find out the answers to those questions? Are they preventing you from making decisions? So these tools allow us, when used in this way, to make decisions earlier. And as you can see, a traditional serial process of developing products, we don't do our design validation until we've gone through the design and produced a product. By us doing these validations earlier, we can reduce the development time. So this is the primary driver for doing simulations early on. And today, the main focus will be on topology optimization. Okay, I'm just going to check my time, make sure I'm not talking too much. Okay, so what does a design iteration look like? So manually, okay, we have some design goals and some requirements to meet. As a designer, in this case, my components might need to meet 1 million load cycles and of 6,000 newtons, and I have a goal of making it 20% lighter. Okay, so how do we deal with that? We create and design the geometry, and then we test it. We either do that physically by making one, or really quickly with an FEA, virtual simulation, and then we review our results, make some proposed changes, change the fillet sizes, gussets, plate thicknesses, and iterate. Very simple. This is how we've always been doing it. So in this case, I have a really brief example of a manual process. I have a bracket. There's a held on the top and bottom of the rear of the T, and it has a load on the end. And as you can see, we have a von Mises stress around 200 megapascals. How do we go about reducing that stress? So as an engineer, you'll ask yourself questions. Can I make a larger fillet? Yes. And I know the answer, that's true. Increase the material thickness. So, but what are the effects of these? What happens if I add a hole? Does adding a hole actually help us? So our virtual tools, as you can see, answer these questions for us live, so we can actually make these decisions before making them. In this case, we can see we've actually reduced the stress in the fillet by 7 megapascals by adding a hole, spreading the stress around the hole. But at some point, if you make that hole too large, we're going to increase the stress and end up with a failure in a different component. So how do you decide where that is? You either use guesswork or you use tools. Okay. So other uses. How else? What else do we use these tools for? Identifying, reducing causes of excessive stress and displacement, we just introduced. We can use it to look at stress concentrations. How do they affect the stress? Inadequate material sizes, loads for given loads, excessive loads, very much the norm. However, in aerospace, often we want to adapt our design to bring our stresses or displacements to acceptable levels. And we want to manipulate our load path. So if I have redundant load paths, the load will go down those redundancies. And they go down there based upon the stiffness of those structures. So the load that a member will take is proportional to its stiffness. So by changing the stiffness of my structure, I change the path of my load and where the structure is loaded. So manually, I have a bracket on the left that has a load on the top and 2 constraints, and I can see some reaction forces. And I can change my load path to adjust how the load comes out at each of those constraints. The object on the right was using topology optimization to do it, but it could have been done in a manual fashion too. Okay, so what if SolidWorks and our tools can remove material automatically? So rather than me telling where the hole has to be and how big, we can use tools. There's a topology optimization tool. It comes from the Simulia technology using the Tosca solver. Helps us minimize mass. It allows multiple simultaneous load cases, and we can add constraints. So we can have stiffness constraints, stress constraints, displacement, and frequency. So in this case here, we can see I have a bracket on the left. And where do I put those cutouts to maximize my stiffness and minimize my mass? I can have a guess and iterate manually, or topology optimization will remove the geometry from areas where it's not needed and create this for us. And Mark will show this example. But I want to move on and talk about unconstrained manufacturing methods. So in this case of the plate, we're using laser cutting to generate it. However, the topology optimization and 3D printing allows us to create geometry that we previously would have been difficult to manufacture. But these tools, as you can see, example from General Electric, put a challenge out to the world to lighten this bracket. We can see topology optimizations lets us dissolve the geometry in an unconstrained method, and it's well suited to 3D printing. Okay, so constrained methods and unconstrained methods. So we'll take a look at each of those examples in just one moment. What we have here is natural frequencies, something we can also work through. And this component here is actually a caliper from a brake for a telescope, a large telescope in South America. Why does natural frequency matter? It shows us the response to vibration loads, which are important in aerospace. Also, the relationship between stiffness and mass is what it will show. It's great soon if you don't have a known load case, you just want to compare relative frequencies. So our natural frequency equals square root of our stiffness over our mass, which basically tells us that our natural frequency is proportional to the stiffness of our structure. So our lower natural frequencies show us where our structure is least stiff. So by doing a topology optimization, looking at natural frequencies, we can actually produce a product that is less stiff for unknown load cases. Okay, so before I hand you over to Mark, I'm just going to talk about the two examples he's going to go through. So the first one is this leg from made out of a piece of profile cut plate using a traditional manufacturing control. I'm going to show you how we can use FEA to dissolve the geometry and put constraints in it that make it able to be made in a way using traditional manufacturing methods. So the tools allow us to do that when that's our preferred output. And then example 2, we're going to use an unconstrained method where we make something more organic that's perfect for 3D printing. You can see the 3D printing can do so much more. So obviously, if your end goal is to manufacture from carbon fiber, then you probably want something more constrained. Okay, and then lastly, Mark will talk a little bit about how we can work with mesh bodies in SolidWorks for manipulation before we send them for printing. So I'm going to hand you over to Mark. Thank you for listening. Feel free to type questions in. I will answer them while Mark is talking, and we'll have some time at the end. Okay, so let me just let's unshare my screen. Thank you.
All right. Thank you, Demi. Thank you, Alan. Hey guys, it's Mark here. Mark Ding. I'm from Central Innovation as well, and I'm one of the application engineers actually supporting the products. I'm having a bit of issue with sharing my my webcam, so I might just leave the webcam turned off. Okay, yeah. So as Demi mentioned earlier on, I'm going to be demonstrating two samples showing how we can use typology study to actually work within SolidWorks and doing design alterations for the existing parts. So open list. Let me start sharing my screen. Okay. Screen 3. Share. Right. Okay. Can you all see my screen at the moment?
It's still black screen. I think it's loading.
Right. I guess yeah, refreshing a little bit on my current screen as well. So hopefully it will come up pretty soon. Right. Okay, can you see my screen now?
I think it's still loading.
It's a bit weird. Let me just quickly reconnect. Sorry for that. There you go. Can you see my screen now?
Yes, I think we can see the SolidWorks. But it's not moving. Hey, Damien, I think mine is off now.
That's okay. I mean, I actually could probably open the files and quickly go through them if you like. That's not a problem.
Sure, you can do that.
It has some technical challenges. Give me 1 second. Let me just find them. I'll be 30 seconds and I'll have those. Okay, I will share my screen again, if it lets me. Okay, guys, sorry about that. There was some technical challenges with Mark there. So I'll go through the first example, like I said, this is a leg from a structure, like a landing leg, very simple, made from plate. The goal is to reduce our weight, maintain most of our stiffness, and not reduce our stress too much. I just need to turn on my add-ons because I wasn't prepared to do this. My simulation add-ons because they're not turned on. You can see my screen though, can't you, Alan?
Yes, no problem.
Excellent. Okay, so in this case, we've set up a study already. It has a simple fixture and a simple remote load, and we've run this. It's not the purpose of just to go through the details of what we set up. We can see we have a few stresses of interest, some around the 90 megapascals, 80 megapascals, and a little bit around the restraint. Okay, and we have a displacement of around 2 millimeters, 2.1 millimeters. So my goal was to reduce that. So you can see on here, I have one I've run before. And we're going to use topology optimization to remove the material rather than doing it manually. So we have the same setup brought over from another study, and we have a goal. In this case, and I think this might answer one of the other person's questions, is we're heading for a best stiffness to weight ratio. We can also do minimize maximum displacement or minimize mass, but we're going to do best stiffness to weight ratio as our goal. And our target is a 60% reduction in mass. Okay. From manufacturing controls, I have put on here on my restraint, a preserve 6 millimeters around my load application and my restraint, so it won't take geometry away from there. I've also set up a minimum thickness of 3 millimeters. And my last manufacturing constraint is how will it remove material? So this option called stamping will remove it all the way through the material in a given direction. So effectively, this is what I'll use for laser cutting. For other alternatives, we can have pull one direction for drafted or molded parts. And lastly, we can have both directions, like a component has a web in the middle. So good for welded components or machined. Ours is done in both directions. So once this has been run, we get a series of results that show us how it's tried to remove them in one direction. And we can edit those and work with them to create our geometry. And we can change our slider to try and remove more or less material based on whatever our goals are. I'm going to stop there, and we're going to talk about what happens once I have this plot. I can save it as a mesh, which I'm not going to because we're going to use something that's nicely machined. In this case, we're going to just show the, if I can find where it lives. It's on here, the simulation display. Oops. And I can plot any of my simulation plots live. And then I can go in here and start creating sketches and cuts to do what I'm after. So you can see how we draw sketches to make my cuts, and we can go ahead and then simulate that independently. In fact, I'd be happy to do that. I don't want to ruin it, so I will copy that study in a moment. Yeah, rerun it. In fact, this one here, because I did it in the same component, I can rerun it and see the results. As you get an idea, we get a live feedback about what we're looking at. I'm going to ignore some of the stress concentrations I haven't got out of there, but we'll look at the ones 90. So we've gone up a little bit on our stress from our 70 to about 130, but it's still well within the yield limit of this component. And my displacement has gone up by 0.5 millimeter. Okay, so in my opinion, that will be sufficient. Okay, so we can carry on doing our work. The other structure we're going to look at, which is, I'm going to find it. This component here is our free from manufacturing methods. So in this goal, unfortunately, I showed you the end result, but that's okay. So we have a model in here. What we've done is created an envelope. Okay, so this is because it's a G-generative technique, we've created an envelope where we can remove geometry from. So rather than generating geometry, we're removing. So this is where we're allowed. We put a load on, and we have some fixtures at the back. Also created a split face, which can be used to preserve regions as you see fit. In this case, I have put the same controls, but this one I put down is remove the mass by 90%. That way I get a better indication of how far I can go with the tools. And we got, again, a preserve region on our areas where we've added loads and constraints. So it will make sure that these faces here will remain intact. And I could have used split faces to do more. So the result of this is that we run through and we have our outputs. I'm going to edit the definition so we can look at it live. And we can change our slider and slowly dissolve the geometry to the point where we're achieving what we're after. And then we can create a smooth mesh. Okay. So simple as that. This smooth mesh then can actually be exported into SolidWorks as a configuration or a new file or whatever we want. In our case, here's the one I've done before. Okay, and you can see I have a mesh file. SolidWorks allows us to work with these mesh files independently. And you'll see there's a mesh modeling tab. This tab lets us create Boolean operations and cuts, and we can work with mesh imports from scans, from topology optimization, from MeshLab, or any other tool of choice. So I'm going to hand you back over to Mark. Feel free to ask questions as you go through. I think we've got a little bit of time left for Mark to, for Alan to go through the end of his presentation, and we'll go through the questions.
Yeah, thank you, Damien. So I will quick share. So I just want to complete the story, right? So you have all this great simulation tool. But then if you choose to use 3D printing to print it, right? The material you use in the simulation and the material you use actually printing might not be exactly the same, right? So how you can trust the printed part will perform the way that the simulator told you. So for that, actually, Markforged has a solution. So just want to share you this case. So this is a load-bearing lifting tools by one of our customers called Danfoss, right? And they see the problem where they have all this nice simulation tool and they have Markforged technology, and they see a gap, right? Like how do I know I printed this part in this design will survive the condition that I'm going to put into the part? And the lifting tool, right? The safety is like the most important here. So basically, because that we have developed the capability to export our pathing, right? So for us, the special thing about Markforged, you will be able to reinforce your part, a certain geometry, a certain area with a continuous fiber. So for example, like in this picture, you can see the blue line is actually representing the carbon fiber routing, and we're laying in this kind of like concentric style, right, to reinforce the whole. So for that, we are able to actually export. Now we export the exact printing toolpath of the part printed by the Markforged printer, and this file will be able to analyze by some material simulation tools and export a file that can be read by FDM software such as the SolidWorks one. So yeah, so here is the result, right? With that, Danfoss is able to simulate this exact same design with print setting using a Markforged printer and understand the failure mode. So they have put the part into the actual test, and the failure mode is exactly the same as the simulation result. And they know this part can survive a 7 times loading with the problem, right? And existing that it will break, and the break is exactly represented here by this FEA simulation. And now they can save a lot of time in testing whether the part will survive or how many fiber they need to add to reinforce the part to get the strength they need. So now you'll be able to design it, and then you can simulate with the software, and then you print, right? And then you use. So you can save a lot of time to wondering whether I want to print a different setting and see which one survive the condition. So you can save a lot of time and material with that export features now offered by the Markforged. Yeah, so finally, just a little bit about Markforged, right? So in Markforged, we do the software part, the material, and the hardware all together to make sure you have a very reliable system, right? We call it the digital forge, so you can trust and rely on the part that came out with the process. So we have a series of different hardware from composite to metal. You can see the material options here. For the composite, we have onyx, fine retardant version, electrostatic dissipative version, and then we have 4 different fiber: carbon fiber, Kevlar, and glass fiber. On the metal side, we have a stainless steel, we have Inconel nail, we have some tool steel, H13D2A2, and also a very rare metal we can print today is a copper, and you can shift that with a Markforged metal printing technology. So Markforged is relatively young compared to SolidWorks, right? We founded in 2013 in Boston. Our founder are all from MIT, and actually we're going public this summer as well. So at the end, I would like to thank Damien and Mark for helping with the webinar, and we have the emails here. So in case you have any questions, you're welcome to contact us or contact directly to Markforged or Central Innovation, and our representative or ourselves will reach out to you. And at the end, I want to thank everyone for your time, and we're close here to our webinar. We have still several minutes, so we can definitely answer a few questions here as well. So just look at the Q&A. So there's a question about the FEA simulation done for the infill. Yeah, so our export feature is also able to export the infill structure. So the simulation will already be able to considering the different infill percentage, right? So after you export the 2-part file from Markforged, you will have a software to convert it to a format that FEA software can read, and you will be very accurately represent the characteristic of the part.
Yeah, and we're doing an FEA on that. You can actually represent that with orthotropic material based upon the structure of the infill. Obviously, if that keeps changing, your FEAs would have to change.
Right. So does the material have certification to be used as an use in aerospace application? Yeah, so there's some requirement in the aerospace industry or the space exploration industry in general, but some agency or organization, they have their own certification process. For example, the part I saw earlier in the US Marine, they actually have an organization to certify all the 3D printing part, and they have their own process, a certification or verification way to approve what kind of part that can be used for end use purpose. For commercial side, I think it's more on the FAA. And I think recently they also changed that to something called NCAM, and we're actively working on that as well. I think there's a question for you, Damien. Let me just look at it. I think Damien, you already answered already, but like in the detailed design validation process using simulation and topology, have these tools been used as a basis for the certification of AM file array part? And do you have any sample case study that you can share?
I don't have a sample case study I can share now. I can send that through to SolidWorks to ask for one. There should be some examples from the Simulia Tosca solvers, because that's used by Boeing and a number of other aerospace companies for dealing with the matrices and lattices. You can represent those as an orthotropic material with XYZ. You'd have to determine the properties. To model each independent piece would be difficult. So normally it would be represented with an idealization. Happy to send me an email if you want to talk about specific application. Email should be on the slide at the bottom.
Yes, Anya.Murphy@centralinnovation.com. Also, there's a question from Meng Hong. What is the largest size of component your machine can produce? Is it applied to all the material? Yeah, so right now our largest composite printer is our X7 series. That is about 330 in length, 220 in the width, and 200 in the height. But if you have a larger part application, please feel free to reach out to myself or our team, and we'll be able to work with you. Will this webinar be available on demand? Yes, I think in a week or a couple of days later, you will receive an email of the recording, so we'll be able to review again all the content that you see today. What material is in use to replace aluminum? That will be our fiber reinforced part, like Onyx with a condensed carbon fiber reinforcement. We have a data sheet to show the strength of our part, which is even better than the aluminum 6061.
So the question from Marco, so when we're using carbon fiber manufacturing, we are looking for the orientation of the fiber and its properties. In that case, to 3D printer, how the simulation setup works. So if you want to simulate an FEA of that, you can, there's actually two modules in SolidWorks. One of them does layups, and you can put your fiber directions for more traditional methods. However, you can create sub-bodies and put an orthotropic material with a direction, either based around cylindrical or orthogonal coordinate systems. So you can have your XYZ calculated from a calculation called the rule of mixtures. So yes, it can be done, but it does have some limitations, and that'd be something we'd cover through training.
Okay, there's another question. Can topology optimization be used to introduce something like a honeycomb grid or lattice structure inside solid part to reduce weight? I think that's a question for you, Namir.
Yeah, I don't believe it has enough control to be able to actually control a type of lattice, because you can control based on your wall thicknesses and the size of your mesh how it dissolves the geometry, but you don't have any more constraint than that. So in some cases it reduces some lattice-like material, but it's not driven to do that.
Yeah, there's a question from Amol George. Does the materials have the certification to be used as end use in aerospace application? Please reach out to our team. We will be able to discuss that in detail with you. Yeah. So I guess that's not too much. There's one more. If you change from aluminum to carbon fiber, any advice for the impact to the cost? I would say you will save a lot of costs in the logistic, machining, and weighting, because if you can print it on the printer, you have more control on the logistic side or the supply chain side, which is introduce a lot of secondary benefits. not just about the cost of the material. Okay, I guess that's it. The time is up, I guess. So thank you again, Damir and Mark, and all the participants to join this event. I think we have shared a lot of new technology and story in aerospace and space exploration sector. And great to catch up with all you. We will have other series of webinar in other industry coming soon as well. So watch out to the announcement from Markforged LinkedIn page or other resources and in the internet. Thank you very much, and I wish you all have a good day. See you next time.
Thank you. Bye.